Okay, so in this module, I want to finish up the general framework for plasticity. We'll talk more about specifics sort of after we've developed this general framework. But I want to begin by just recalling a couple things that we've talked about in some of the previous modules. So let's just say we want to recall. And the first thing we want to recall is that we'd said that we can't change the plastic strain without changing the internal variables. And of course that's obvious if you think of plastic strain as an internal variable, but in general we prove that with the consistency condition. And so we wrote something that looked like d epsilon ijp, so the increment in plastic strain would be equal to some array of second order tensors we call it hij_k times dqk, right, where dqk was our increment in our internal state vector. And let's go ahead and call that equation 1. We'd also said at the end of our last module that the change in the internal state vector dqk during any sort of a stress increment or a plastic strain increment is going to be equal to a scalar quantity b times some direction that we'll call tk. So tk, if you remember, the reason we separated them out like this was because tk was a function of only sigma and q, and this is vector, some vector direction. Okay, and then b, right, was a scalar magnitude. Okay, so scalar magnitude, and as a result, it was a function of not only stress and the internal state vector q, but also of the stress increment d sigma. Okay, let's go ahead and call that equation 2. So that's hopefully something you remember from some of the previous modules. Okay, I'm going to ask you to recall the consistency condition again. So recall the consistency condition, right? And all that said was that f is not changing, so it stays equaling 0 when yielding is happening. So recall the consistency condition. We could say that df equals 0, right? Or equivalently in rate form that f dot equals 0 during yielding. Okay? And our goal here is we want to come up with some sort of a flow rule. So one of the outcomes of the consistency condition that we showed last time was that we could write that the partial of f with respect to sigma ij, d sigma ij, right? That's the quantity we looked at to see if yielding was happening when f equals 0, right? So if that quantity was greater than 0, then we knew we were loading, or we would be inducing plastic deformation. If it's equal to 0, then we're moving along the yield surface but not loading the yield surface. And if it's less than 0, we're unloading, and we in both 0 and less than 0 case we behave elastically there. So but we said that the consistency condition ensured that during yielding we could write that the partial of f with respect to sigma ij times d sigma ij was equal to the partial of f with respect to the internal state parameter times the increment in the internal state parameter, which if we now go ahead and substitute 2, so write substitute 2 from above into there, dqk now looks like b times tk, so we can write this as negative partial f with respect to qk times b times tk. Okay, let's call that equation 3. Okay, so the first thing we want to do here is solve for b. Okay, so let's say solving for b. Okay. All right, solving for b, we can write that b is equal to negative partial f with respect to sigma ij times d sigma ij divided by partial of f with respect to qk times tk, right? Let's go ahead and call that equation 4. So nothing fancy there, I just rearranged equation 3. So I can now substitute 4 back into 2. Okay, so substitute 4 into 2, right? And all 2 was the definition of dqk. So that said that dqk is equal to, and now I'm going to write b, it's b times tk, right? So b is going to look like partial of f with respect to sigma ij times d sigma ij divided by partial of f with respect to qk times tk, right? That's b. And then we have to be a little careful. I wrote it a little sloppily. Since down here k is my repeated index, it's a dummy index, I'm going to go ahead and change that to make it L so that our rules for index notation is followed, okay? Because we want this k to still remain to be a free index. So we have a scalar in the numerator, a scalar in the denominator. This gives us a scalar overall multiplied times tk, okay? We'll call that equation 5. And now we're going to go ahead and substitute equation 5 into equation 1, which was the original relationship that we had between the plastic strain and the internal state variable. Okay, so let's write that we can go ahead and substitute 5 into 1. Okay, and we get the following. So we began there with del epsilon ij plastic, so the plastic strain increment, going to be equal to Hij and then this quantity is dqk, which we just wrote. So dqk then looks like negative partial f with respect to, I have to, similarly here, I can't use ij anymore because I already have that as my, they're not repeated, right? So these are free indices. So let's go ahead. We don't want to use L because, or K, because I already have those also in there. So let's say Mn in this case times d sigma Mn, right? I'm free to switch around any of my dummy indices. And then over partial f with respect to QL times TL, right? So that's B. And then this whole thing times TK. So I have K in my repeated index, I have L in a repeated index, M and N are repeated, and so my free indices are I and J. Okay? I know it's kind of algebraically messy. We're going to try to clean it up a little bit here in a minute. So let's call this equation 6. Okay, so I want to simplify this a little bit. And I want to do that by introducing another quantity. Okay, so let's simplify by introducing another quantity. Okay, and that quantity is going to be psi, and we'll call it psi ij, and say it's a function of sigma and q. So we can pull out from here anything that might be a function of sigma and q. And so what we could write it as is, how about negative hij times k times tk divided by the partial of f with respect to ql times tl. Okay? And I want to remind you, why can we do this? Because, just recall again, right? The whole point of breaking the change in the internal state parameter dq into a magnitude and a direction was because the direction t is only a function of sigma and q, right? And so that fits in with our this newly introduced function. And we also know that the scalar function f is also only a function of sigma and q, right? It's not a function of dq. Okay? So let's go ahead and call that equation 7. So that looks like I took this denominator, this vector, multiplied it times here, and then pulled out this sort of double dot product or a second order contraction here. Okay, so now what do we do? Well, we're going to substitute 7 into 6. So substitute 7 into 6. Okay, and what we do when we do that is we get d epsilon ij p, the plastic strain increment, going to be equal to psi ij, which I'm going to remind you now is a function of sigma and q, right? Times now this other quantity that I pulled out, which looks like partial f with respect to, or partial f with respect to sigma mn times d sigma mn. Okay? Hopefully that's straightforward, and we'll call that equation 8. Okay, let's think about this for a minute. So this quantity here, right? We already know that in order for yielding to happen, that quantity is greater than 0, and it's a scalar. So let's note that it's a scalar that's also greater than 0. Okay. So what does that mean? That means this term, this psi ij term, well, it must define the I'm going to put in quotes, the direction of the plastic increment. Okay? The plastic strain increment. Okay? Why do I want to say that? Well, if you remember in the last lecture, what we talked about was that during plastic deformation, it has been demonstrated experimentally that the plastic strain increment is normal or orthogonal to the yield surface at whatever point sigma and q we're at. So, okay, so let me write that down. I'll just say that recall that that d epsilon ij p, the plastic strain increment, must be orthogonal, okay, to the yield surface, which we define as f of sigma and q, that's supposed to be a tilde, equals 0, right? Must be orthogonal to the yield surface. Okay, so that's number 1. What else do I want you to recall? How do we define a quantity that's orthogonal to the yield surface at any given point? So recall also, right, that the partial of f with respect to sigma ij is orthogonal to f equals 0. Okay, so what we know is that the plastic strain increment d epsilon ijp must go in the same direction as this gradient quantity here. So this gradient quantity sort of can be represented in this psi ij as the direction, so to speak. Okay, so all of these features imply that I can write that psi ij sigma and q, well, that could be equal to some function that's a scalar valued function that must be a function of sigma and q times this partial. Okay, why do we know that? Because this is orthogonal to the yield surface. Okay. And this quantity, this g, we call this the scalar hardening function. let's go ahead and call this equation 9. And we'll define some things here. So in equation 9, F is said to function as what's called a plastic potential. So it's said to function as a plastic potential. I know that it could be a little bit of a foreign concept to everybody. I'm not at this time gonna detail sort of potential theory, but when you see a scalar function that we can take a derivative from and obtain sort of another function from, like this case, we can take the derivative of f with respect to sigma ij, and we now get the direction of epsilon ij. We typically say that that the function that we took the derivative of is the potential function, or is a potential function. Okay, and in fact, if this is the case, then the constitutive behavior that this describes, constitutive behavior that follows 9, it has a specific name. So constitutive behavior following 9 is called an associative flow rule. Okay. So I did it this way so that we could link this development to everything we've done in the past. It's also possible to say, well, I still want to use this idea of a potential, but I don't want it to be the yield function f. I want to call it something else. Let's call it g. In that case, then it's still a valid formulation, but in that case, the flow rule is called non-associative. Okay, so let me write that down. So if a different potential from f, or besides f, is used, okay, let's say maybe g, right, still a function of sigma and q, okay, then the resultant flow rule is going to be called non-associative. So the resultant flow rule is non-associative. Okay, just some definitions. Okay. In general, in this class, we're going to work with associative flow rules. In the case where we had that, then we would write psi ij, again, a function of sigma and q, is equal to g, still the same scalar hardening function, but now it's going to be the partial of g, some function besides the yield function with respect to sigma ij. Okay? And we can call that equation 10 if you like. I know this is kind of theoretical right now. One thing I'll mention, and I'll write down here in just a minute, is that we're not trying to compute the scalar hardening function, and we're not trying to compute the yield function. We are assuming that those are given and characterized from experiments. So we're just using those in our formulation to determine how plastic strain evolves under some load scenario. So let's go ahead and plug in the associative flow rule from equation 9 back into equation 8. So let's say in the case of an associative flow rule, so in the case of an associative flow rule, okay, we can substitute 9 into 8, right, to get that we can write that the plastic strain increment d epsilon ij p is equal to partial f with respect to I can say sigma now kl d sigma kl, times G, which is a function of sigma and Q, times the partial of F with respect to sigma ij. Okay? So there is your flow rule that depends on the stress increment. Let's go ahead and call that equation 11. Okay? So this is the flow rule. And it's for the associative case. Okay? It looks a little different than the flow rule we did previously, right? Because we talked about incrementing in strain, and now in this case, I'm actually incrementing in stress, right? I have a d sigma KL term that's driving how much magnitude that the plastic strain increment is. I still want to remind you, though, that the above equation, so equation 11, that's not very good, 11. Equation 11 is still only valid in the case that we had defined for the other flow rules. So it's still only valid, right, for the case where F of sigma and Q is equal to 0, and right, both things are required. The partial of F with respect to sigma ij, d sigma ij is greater than 0, right, that it's loading. Okay, so that the typical restriction still holds for when this flow rule works. Okay, and I want to remind you also that the following quantities need to be known. Okay, they're not computed. We're not trying to determine them, or they don't have some sort of theoretical derivation. We have to know from experiment. So, so the following quantities must be known. Okay, via either experiment, characterization, or literature, if you like. Okay, some other place. This isn't something that we're computing. It's like trying to do to predict the stress response in the elastic case without knowing the modulus, right? You just don't do that. You have to go do a test to find the modulus. Okay. So the feature here is they're not computed a priori. Okay, we have to go look them up. Okay, so those quantities are, number one, the yield function. Okay, and in some sense you'll decide that as the user. So the yield function is, right, F, which is a function of sigma and some set of internal variables. Okay, number two, the hardening function. It's a scalar. Okay, so remember that's also G as a function of sigma and Q. And then sometimes, if you have a non-associative rule, you'll also need an additional plastic potential. Plastic potential. Which would be also some G as a little g I'm writing here. It's a function of sigma and Q. And I'll just note here, this could be just F, just the yield function, okay, for an associative flow rule. Okay, so again, I know that some of this stuff probably is a little fuzzy in your mind. I don't have an easy way to solidify it until I at least show you the framework first. So let me again just try to, just in the name of summarizing some things, I'm gonna just list off some things that we've already talked about. So here's a bit of a summary of sort of the general framework for plastic behavior. So number one is that we still decompose the strain, right, as a additive elastic plus plastic component, right? So we could write that the strain must be equal to the elastic strain plus the plastic strain, right? Or in differential form, we could say that the increment in strain is equal to the increment in the elastic component plus the increment in the plastic component. Okay, that's hopefully straightforward. Number 2, we have what happens to the elastic strains? Well, that just follows Hooke's law. Okay, so in that case, we have that epsilon ij elastic, right? It's going to be equal to 1 over 2g times sigma ij minus nu over e times sigma kk delta ij, right? And by now you can invert that if you wanted to write Hooke's law in terms of stress equals something with respect to strain. Okay, and the third sort of feature that I want you to be reminded of is that we had a yield function, right? And that yield function looked like f as a function of sigma plus some internal variables is equal to 0 on the yield surface. Okay, and we had a couple conditions. When we had the partial of f with respect to sigma ij times the stress increment d sigma ij, when that quantity is greater than 0, we said that that's loading, or it's maybe yielding. Okay, and what that means when we do that is that d epsilon ij p, we write down, this is when we invoke the constitutive law we just developed. It looks like the partial of f with respect to sigma kl d sigma kl times g, which is a function of sigma and q, times the partial of f with respect to sigma ij. Okay. The other case is where the partial of f with respect to sigma ij times d sigma ij is less than or equal to 0, right? Then it's either neutral loading or it's unloading. In either case, that behaves elastically. Okay? Hopefully that was fairly clear and a little bit of a compact summary of what you need to know for how a material is going to behave under loading. At the moment, what you don't know is maybe what the form is for all the yield functions, or maybe the scalar hardening function. But hopefully the other operations are all fairly straightforward.